My name is Dave Butler. I'm a safety engineer with Exita. I've been mostly a software development engineer most of my career. I switched to safety engineering a few years ago, and the software development I've done in my career was in mostly in process control. I developed process control products. And I have used UML to develop executable prototypes as well for design purposes, So I've used UML to do design work as well as developing executable prototypes. That's what I'm trying to say. I've also worked in the telecommunications industry and a little bit of work in consulting for software for medical device development. So that's my background, and I'd like to just get started here. Quick overview of what we're going to be talking about for the next hour or so is, give an introduction to some of how the meeting is going to go, and I'll talk about supporting concepts. I'll talk about common notation elements that are used in UML and the diagram types for UML. I'll also try to give you a little bit of background into how UML is used, as well as where you can go for more information. So what are the objectives of this webinar? Lend perspective about what UML is and what it is not, to introduce you to the notation, of course, and to provide you, as I said, with some resources that you can use to further your understanding. So what is UML? UML is a standard modeling notation. It's often confused with other concepts. It's defined by the UML specification, which is a standard maintained by a standards organization. I'll talk about that in a little bit. And it is also extensible by modelers. So it's not just the standard notations you can use, but you can use the notation they give you to extend concepts in UML. What is UML not? UML is not a workflow. It's not a modeling tool, although it is supported by modeling tools, and it's not a methodology, where a methodology would be similar to a workflow in that it talks about how to use the notation to do design in your specific way. So you can sort of customize or tailor its use for your purposes. Quick history of UML. I'm not going to go through this chart. I just wanted to present it to show how complex things were back in the day. In the 1990s, there was a proliferation of methodologies and notations that were being put forth as the best way to do things. Many of them overlapped quite a bit, and some of them complemented each other. So Booch, Rumbaugh, and Jacobson, also known as the Three Amigos, pulled together what they termed to be UML, or Unified Modeling Language, around in the early 90s. And it has since been developed and added to. I believe the latest version is 2.41 at this point. UML 2 was a big step up, and from UML 1, I think that was in around 2005, UML 2, if I go back here. Yes, around 2005, UML 2 was released, and it has stayed, fairly stable for the last several years without much change. So, what can UML be used to do? Basically, you can use UML as a notation, and you can use it in a modeling context. So, it's in a way you could say it's sort of flexible that way. You don't have to model with it. It's a good means to convey design concepts in a standard way. Any kind of, to illustrate my point, any kind of tool can be used, including pencil and paper. So you could use pencil and paper drawing software like Microsoft Paint or Microsoft Visio, which simply draws shapes, or you can use modeling software like Rational Rows, IBM's Rhapsody, or Microsoft Visio has a plugin that allows you to do modeling as well as just drawing. And I'll get into the differences between modeling and drawing in a few minutes. It has software. The UML has software development origins, but it can be used for many types of technical analysis and representation, or even non-technical. It's also been extended to do things like systems design. So the difference between diagramming and modeling. In diagramming, elements are actually part of the diagram. So when I say element, I'm talking about something like a class, and we'll talk about classes later, but that's sort of one of the basic elements of UML. And I'm sure if you are aware of software, you're aware of classes. So elements are actually part of the diagram. So if you have a common element, such as a particular class type or class name, and you represent that in two diagrams, that element would be represented or would be stored in both those diagrams. In other words, it would be stored redundantly. So elements are connected at the diagram level. They're not connected across a whole model, and they're simply formatted shapes and text on a page. Whereas modeling has sort of a back end or a database behind the diagrams. The diagrams are actually part of the database in many cases, but the elements that are represented on the diagrams are stored as database elements and can be reused so that you have non-redundant storage of the definition of an element. And they're also connected at the model level. So there's a view, and that view might be, these three bullets are sort of structured in a model view controller type pattern, and I'll show you a diagram in a second that shows it pictorially. Model view controller is a design pattern that's used in software development, and I'm trying to relate that to UML here and how modeling is done. So the view in this case would be diagrams and dialog boxes that present data from the database data. And then the controller would be the actual modeling tool and the rules in the modeling tool to control the data. So for example, Visio UML might have a way to enter all that data in both a text formatted way and a diagrammatic way. So this is sort of a picture of what I'm talking about. The top row there is the view, the middle row is the controller, and then the bottom row is the repository model. And on the right-hand side of the diagram is the diagramming sort of method, and on the left is the modeling approach. So you can see in the repository box for the modeling side, the diagrams share the elements that are stored in the model, and the diagrams themselves are also stored in the repository. The diagrams in the repository box below are not visible. They're just data in a database. The diagrams in the top row, diagram 1 and diagram 2, those are what are visible on the screen. So you can see the relationship between those and the diagrams in the repository are a renders relationship. So what is UML used for? It can be used in a lot of different ways. It's useful for requirements management. There are use case diagrams, so you can do use case analysis with it. It can be used in a system design, for system design applications. So you can design deployment diagrams, communications diagrams, and show both the structure and the behaviors of systems. This is where I was going to mention that SysML is the extension to UML for systems development. That extension is actually another specification, but I believe it uses all of the same notations as UML, but it extends UML with other types of elements that support systems development a little bit better. You can also use UML for product, hardware, software architecture design. It shows external interface specifications, internal components, relationships, interactions, behaviors, structures, so on, and we'll get into all that detail. And then software design shows sort of a deeper design as well, including stateful designs and more detail in terms of the level of concepts in software and or hardware design. There are many different kinds of tools available, many more than this even. I just wanted to note a couple of them. I mentioned earlier Rhapsody and rational rows. They're both IBM products. I'm pretty familiar with IBM RAFC. That's the tool I use to do the modeling work that I've done in my career. They were owned by iLogix, bought by Telelogic, and then by IBM. So even though ROSE and RAFC are somewhat competing products, they're both owned by IBM. Altova has a modeling tool called UModel, and as I mentioned, Microsoft has sort of an aspect to it that's a UML modeler in Visio, and I use that quite often because it's very readily available. If you have Microsoft Office with Visio in it, you probably have the ability to model UML right now. And so you don't have to go out and buy a product or anything. If you wanted to play around with these UML concepts, you can use Visio to do that. Star UML is an open source. It hasn't been kept up to date with the standard, so I wouldn't recommend using that, but I did want to mention it. And many other tools can be found at the links that I've given here. I also wanted to mention that there will be a PDF made available after this webinar is over that you'll be able to download the slides, and you should be able to get those links from that PDF. Some other resources I would give you. I've been through some of these, and some of them are pretty good. OMG.org is Object Modeling Group, and they are the maintainers of the UML specification. You can go there and download the specification itself for free. There's different aspects of that specification, so it might take a little getting used to what they've done. They talk about meta. There's sort of a lot of meta specification, and then there's the specification of UML itself, so it takes a little bit of getting used to understand those concepts. I'm not going to get into that here. Next section will be supporting concepts. So these aren't necessarily notations per se, but they're things to understand, maybe some terminology and so forth. In the specification, the UML specification, they talk about a meta class, which represents a modeling concept. So the meta class, well, I'll let the specification speak for that. It gets a little complicated, so I don't want to really dive into that too much. An element has specified graphical and text presentations. So there may be more than one presentation of an element type. Element is sort of a generic name for an entity you can plunk down on the diagram or store in the model. An element has name, attributes, the ability to have one or more stereotypes attached to it, one or more tags attached to it, and there may be a couple other things that you can that an element has. If you know object-oriented programming, you could think of this as sort of a superclass or base class, and then these are some of the attributes, some of the properties that base class would have, and other modeling elements would be derived from this element. Other supporting concepts are classifiers, events, and behaviors. These are also elements, but these are the three basic categories. So a classifier describes a type of object. So again, a class would be a classifier, an interface would be a classifier. Interfaces are really specialized classes. And a deployment node might be a classifier, and there's some other ones. Events describe a set of possible occurrences of events, really. So real-world events, or in software events, a timer tick, a message, the receipt of a message, the occurrence of an error, something like that. Behaviors describe a set of steps that are taken to execute some logic. Classifiers, events, and behaviors, you could think of them as sort of reusable types. So you can have multiple instances of a specific classifier. So for example, if you have a class named Dave, then that Dave could be instantiated multiple times. Or better yet, a class named Person, you could instantiate a Dave class, a Bob class, a Norm class, and so on. And that's what this next bullet says, that classifiers, events, and behaviors, when you instantiate those things, you get objects, occurrences, and executions. And those terms are actually used in the UML specification. Okay, so I've mentioned stereotype before. What is a stereotype? Basically, this is that one of the extension mechanisms that UML offers to extend the meanings of elements. So any element can be stereotyped. As you saw earlier, an element has a stereotype ability built into it, and if that's the superclass, then anything derived from it would also get that same ability. And it extends the standard semantics of the model element. And there are some standard stereotypes, and then you can also user-define stereotypes. So some standard stereotypes, the main one that I want to point out is an interface. An interface stereotype. Stereotypes can be interpreted by tools to be rendered in different ways. A standard stereotype, the interface, the rendering of that interface is actually specified by the UML as a lollipop. And I'll talk more about that later if you may or may not be familiar with that. So let's see. Right, so stereotypes can be used by tools, as I said, for rendering, but also for semantic checking. If a tool understands a particular stereotype, whether it's standard or user-defined, it could leverage that sort of piece of data about the element to execute rules about, semantic rules about how elements play together or what that element is supposed to be responsible for and so on. So some good examples of user-defined stereotypes might be TCP/IP might label a connection between two elements. Windows PC might label a node in a deployment diagram to further indicate that it's not just a node, it's the type of node that it is, it's a Windows PC. DLL might indicate that you have a dynamic link library. That might be a label on or a stereotype on a component. Okay, so UML diagrams. There are many UML diagrams. I believe it's 13 at this point. I don't know if I'm representing all of them here. Most of them will be represented, certainly the most important ones. There's many types. There's class diagrams, sequence diagrams, state machine diagrams, and so on. And I'll talk about each one of them. If I don't have 13, I probably have 11 or so, maybe. Each diagram has its own notation and semantics. Each diagram has its own conceptual purpose. Some elements can be used on multiple diagram types. So, a class diagram and an object diagram might both be able to represent a class on that diagram. And let's see. Class, let's see. Oh, okay, I said that already. So yeah, that second bullet is another example. An interface might also be able to be used on a component diagram or a class diagram to indicate an interface. Packages. A package is really just a collection of model elements, and you can name that collection. And it's used basically to group and organize in your model. You can also diagram packages in a package diagram, and there's certain semantics about how you would do that. How packages are related together, and again, I'll talk about some of that later on. Why would you want to use package diagrams? You might want to collect your source code modules to show which source code files go into a module, which modules go into a component, which components go into nodes, those kinds of things. And there are diagrams that show those concepts differently than in packages, but you might want to show the source code for and how it relates to those concepts. Okay, so common elements. These next set of slides is a good solid portion of the presentation, and basically what I'll be doing is going through each of the main elements that can be used on different diagrams, regardless of what diagrams they can be used on. So I'm just going to explain sort of the primitive element notations and what their purposes are. So a class is basically meant to be a reusable, as I mentioned earlier, it's a classifier, and it's meant to be a reusable type that can be instantiated in multiple places or reused in multiple places, and has a name, attributes, operations, receptions for events, and so on. This is a snippet from let's say, a class diagram or an object diagram that shows instances of I'm sorry, this does not show instances. This shows a class, mousetrap, bait, woodblock, spring. Those are the 4 classes that are depicted on this diagram. And it shows their relationships through what are called associations, and I'll talk more about associations later. So you can see that a mousetrap has a base, which is of type woodblock. It has a spring, which is of type spring, and it has bait that's associated with it. Each of the classes also has attributes, so you can see that the hammer, holding bar, catch, and state are attributes. Also, attributes are base, spring, and bait for mousetrap. So you can see that attributes for the class are depicted in 2 different ways. One is outside of the depiction of the class, or outside of the rectangle, and the other ones are sort of inside the rectangle. That doesn't mean that the outside ones are public or private, and the inside ones are private. It just means that they're depicted in different ways in the drawing. The bottom compartment of the mousetrap class in this diagram shows a set and snap operation. And the very last one is a reception, which there's an event called bait taken, which that operation will handle. It's been stereotyped, which between the 2 pairs of less than, and greater than, it says signal. That is a stereotype. That is how a stereotype is depicted on a diagram. It's not required to be depicted. Even if it exists, it's not required to be depicted, but it may be shown. So that's a class. Classes are sort of the workhorse of object-oriented design. So again, attributes are part of a class. They're the members of a class or the properties of a class. Those are 2 different names, other names or synonyms for attribute. Each attribute has a name, a type, multiplicity, visibility, and initial value. They could have other traits. What's the relationship between a class and an instance? If you recall earlier, I was talking about the different types of elements. For a classifier, you would instantiate a classifier. So a class is instantiated into what's called an object. So in this case, an automobile class is instantiated to create Dave's car, which is an automobile. So if you see the rectangle on the right, I want you to notice a couple things. In the rectangle on the left, the type name, or the class name, is automobile. On the right, Dave's car is the instance name, followed by a colon, followed by the type of class that it is. And again, the tools will allow you to show as much or as little information about what you're depicting, but if you're going to depict it, this is the way it needs to be depicted. The make, model, and engine size are attributes of the automobile, and in the instance class on the right, they're given initial values: Nissan Altima 245 horsepower. Also notice that the instance name is underlined, including the type name if that's presented, whereas the class name in the class on the left is not underlined. The minuses in the attribute compartment indicate private variables. The pluses indicate public operations. So an automobile has a start, stop, and accelerate operation, as well as the make, model, and engine size attributes. A stereotype of an abstract class. An interface is a stereotype of an abstract class. And again, interfaces can be represented in different ways. This is the first method of presentation. An interface is basically an abstract contract which is provided or required. And those are terms that are used in UML by a realization element. So on the right-hand side, you can see there's a proximity interface in the example given. I'm sorry. I take that back. The proximity sensor has an eye sensor interface, and the triangle at the end of the dotted line there indicates that proximity sensor realizes the eye sensor interface. So in other words, it's providing an interface to users. On the left is a class called theft alarm, which uses the eye sensor interface. And in this diagram, it's showing that it uses the proximity sensors implemented version of iSensor. It also shows that the iSensor is an interface using the interface stereotype, and it shows the operations that are provided by proximity sensor because it implements the iSensor interface. Interface has name, attributes, operations, and can also have receptions, which are basically event handlers. So here's the this slide is intentionally put in here to show the different presentations of, alternative presentations of an interface realization and use. So a tool may choose to implement all of these or only some of them. So you should be familiar with all of them. On the left is simply the one we just talked about, with the exception of the fact that the generalization relationship between proximity sensor and iSensor shows the realizes stereotype. That's the stereotype notation. The one in the middle on the top there shows that theft alarm is using iSensor, but you'll notice that iSensor, instead of being represented with a generalizes and a class, generalizes association and a class, is represented simply by a solid line with a circle at the end of it. That's called the lollipop notation, and it obviously has value in that it can sort of compress your presentation elements. The ball and socket notation shows not only that an interface is provided by component 2 in this case, but also that it's used by or required by component 1. So that's the ball and socket notation, and that's used on different kinds of, mostly on component diagrams. Okay, objects. As I said, objects are manifestation of a class. They're called instances or objects, and an object name is underlined. Type name may or may not be displayed. The object name may or may not be displayed. And the attributes take on, and what I mean by object name may or may not be displayed, that might be a little confusing. You would think there wouldn't be a name, but what I meant was you might show a class name that's underlined to show that this is an instance of a class, but it's one that I'm not going to bother with a specific name about. And there are cases where that comes in handy. Attributes take on specific values when you instantiate a class. Obviously, they can have initial values, as I discussed before, but you can change those values as your program runs, or as scenarios play out, I should say, because it's not just about software. State is specific to the object. So state might be declared you might have state variables declared as attributes in the class, but they're used in the object. Okay, so these are just more examples of how to present instances of classes or objects. So on the left you see the class without the underline. In the middle you see Dave's car with automobile, only showing the attributes even though it may have operations. The initial values are displayed. On the right, you don't even have to display the attributes. You can display just the instance name and the type name. You can display just the type name, or you can display just the instance name. So this shows flexibility at the presentation side or the diagramming side. Associations. Okay, so associations, we sort of alluded to them. Those are the lines that go between two elements, and there's many kinds. And the different kinds of associations are indicated by different drawing shapes, I guess you could say. An association has named ends. It has navigation, so you might have an arrow going one way or both ways, or no way. You might just have a single line between them. It can be stereotyped, as all elements can be. It can have multiplicity to indicate how many of the things it's connected to at that end there are. So you might have an object instance that's connected through aggregation to a set of object instances on the right, but you would indicate that by showing that second instance, but then you would put a number there, 3 star to indicate 0 to many. You can have 1 to many and so on, and we'll get into a little bit of that, I believe. And then visibility also indicates whether it's a public or private connection. So these are some of the association kinds you can have. The first one is sort of a non-specific. You're just associating two elements, showing the association. You may or may not name it. You may or may not care about any of the attributes other than to show that they're related somehow. For different levels of analysis and design, you may have different amounts of information. So early on, you may want to just draw an association. Many tools allow you to convert that association into the other kinds of more specific associations. So that can be a flexibility advantage. Dependency simply shows that one element, the one on the left, depends on the one on the right. So the dependency goes in the direction of the arrow. You can label dependencies to show the type of dependency, and you would read that as the left one is whatever the dependency type is dependent on the right one. Generalization shows the inherits relationship or the specialization relationship. It also represents the realizes relationship, meaning implements. And again, that is a stereotyped generalization, as we saw with interfaces. The next two are aggregation. There's two types of aggregation. One is shared aggregation. The other is composite aggregation. The shared aggregation represents ownership by the thing on the left of the thing on the right, but not necessarily from the time of construction. So if the thing on the left is constructed, if the instance is instantiated, it may or may not be instantiated with the thing on the right. If it must be instantiated with the thing on the right, then that's composite. So in other words, they live and die together. The element on the right and the element on the left are created and destroyed at the same time, and they're forced to be created and destroyed at the same time. So it's sort of composed of that element or those elements, depending on the multiplicity. And then you can have, as I said, you can have stereotyped aggregation. I just showed one down at the bottom, 4 to 20 milliamp, for example, connection between two devices. So this is non-specific associations. I just wanted to show how they're represented. There's the named ends, the vehicle categories on the right. The multiplicity on the right is one. It shows that a vehicle has one vehicle type. It's called a binary association. A line with no arrows or no other adornments on either side is either non-specific, interpreted to be non-specific, or it's interpreted to be communication goes both ways. So you can think of it as an arrow on both sides. A vehicle type talks to a vehicle, and a vehicle talks to a vehicle type. And when I say talks to, that can mean any kind of interaction you want to think about. In the case of vehicle and vehicle type, this is probably more like a non-specific association. Dependency association. This is an example of the rendering of how you would use the dependency association. In this case, it's an instantiate association. The class on the left is called car factory, and it's a factory class which can produce cars. So this may or may not be a software example. Could be a real factory, could be a software factory that produces car instances. So let's see if there's anything else I want to say there. No, I don't think so. So here's an example of generalization. Generalization is, as I said, the inheritance or generalization specialization association. There's a lot of different terms in software and object-oriented design that mean the same kinds of things. So I'm trying to use all of them, actually. The ones in the slides are generally the ones that are used in the specification, the UML specification. Okay, so generalization in this case is shown as a shape class, which may or may not have attributes, other qualities, operations, event handlers, so on. And then polygon, ellipse, and spline are derived from the shape object, so that you can store these the type definitions for the attributes and operations and so forth non-redundantly, so that a polygon, ellipse, and a spline all polymorphically represent shapes. So you can treat whatever instance you create from a polygon or an ellipse or a spline, you can treat them polymorphically as shapes. Shared aggregation association. This again is the open diamond and indicates that a B is created after an A is created. Could be one or more B's. depending on multiplicity. It's indicated by the open diamond. The arrowhead indicates that A owns B, or has a B. The dot is new to me, and I included it only to show you that there may be some kind of a notation that the specification requires or allows that I'm not really 100% sure of exactly what that's supposed to mean, to be honest. It may mean that the association itself is owned by A, but I'm just guessing at this point. Composite Aggregation Association, basically the same thing as the previous one, but in this case, a woodblock would be created when a mousetrap is created, and a spring would also be created at the same time the mousetrap is created. Maybe the constructor, creates it at that time. Maybe a constructor requires you to pass in the woodblock and spring in order to create a mousetrap. It is all a matter of interpretation. So again, the mousetrap must have a woodblock and spring. And again, the arrowhead shows who owns what. In this case, the mousetrap owning the base and the spring. Events. An occurrence, as I said before, it's an occurrence of interest at a specific time and location. So at some point in time, something happens, and this is the way to model the thing that happens. You would give it attributes, importance of an event. You might have messages that are being exchanged, and when they arrive, the message itself is an attribute. Those kinds of things. There's different kinds of events. There's call events, signal events, change events, and time events. And they're used in different contexts, obviously. And again, an event can have attributes and also can be stereotyped. Components. A modular system, let's see. So yes, a component is a modular system part that encapsulates its contents. That's sort of the definition from the specification. And it's replaceable within its environment. The idea of a component is that it's able to be used to build up systems in a structured way. So it's more of a structure type component. And it can be deployed in an execution environment. So it can have behavior. So a component has names, ports, interfaces that it provides. It may require interfaces, and it has a realization body. I'm not sure what got cut off at the end of that there. Yeah, I can't really read it. I'm trying to read the sidebar here. Yeah, sorry about that. I probably should have made that text smaller so I could read that, but I can't read it. It's not that important. An assembly connector. Okay, so an assembly connector connects two components, and again, with in this case, this is the ball and socket presentation of an interface, or of interfaces. So the ball part of it, or the lollipop part of it, is the provided interface. The socket part of it is the required interface, so order requires the interface, which I don't have a name for the interface on here, and it really should have a name, and that's a mistake on my part. Oh, it's an orderable item. Generally, you would only see that once in the middle there. I guess it labeled both the required interface and the provided interface. I'm not really that used to using that particular presentation technique. So there's an orderable item interface that is shared between these two. One uses it, the other one provides it, and it's between two components. In this case, the colon order and the colon product are component types. And you can see the square box that connects them to the component, the interfaces to the component. Those are called nodes, and may or may not be, useful in the context that the context of your design. So a component might be a physical component, in which case it has I said they're nodes. They're not nodes. They're ports. I misspoke. I apologize for that. But a port may be actually a physical port, so that would be like a connector. So you might have a serial interface on a computer, for example, and that might be represented in a diagram where the component is a computer. You might call that a system component, and that computer has a serial interface that's represented as a port on a component diagram. This is the way we would represent that. And then the interface may represent a particular protocol that goes over that serial port. So that would be an example of how to use assembly connectors to connect ports on components. Actions. Actions are basically elements of executable functionality. They have input, output, and process in the middle. And they basically contain behaviors. The inputs may be the outputs of a prior action. And the actions can include operations, and send signal is a way to raise an event. So in this case, that would be a signal event. I mentioned the different kinds of events before. So you might get to a certain point in your procedure or your action, and you might decide that you need to raise some kind of an event that goes off to a state transition or state machine and fires state changes. Direct behavior invocations can also be used, which would be just inline logic, basically. Operations and signals can be bound to activities, state machine transitions, or other behaviors. So an activity is sort of a higher level interaction and can contain actions, and it coordinates them with a certain set of syntax that allows you to coordinate their sort of parallel execution or sequential execution and so forth. And I'll show you all this when we get to diagrams. After this section on elements, there'll be another section on diagrams that will sort of tie all this stuff together. It can model multi-threaded behaviors, control and data flow models, modeling elements, and events can be fired that affect external entities. Control flow is supported. I think I already mentioned that actually, and exceptions, which are basically another kind of an event, are also supported. Okay. There's a lot of different activity kinds or activity types. Okay, so these are not activity kinds per se. These are activity element kinds. So types of activity elements. So an accept event action, a send signal action, an action itself just executing normal logic. Activity final nodes, which indicates the end of an activity. A data store is a place where data can be stored in the activity. A decision diamond, and you'll see that allows you to create two different paths depending on a condition. A merge node, a fork node, and a join node all have to do with parallel execution. Initial node is where you start an activity once you initiate it. And an object node, I'm not 100% sure what that one is. I got that one. I'm not familiar with that one. Used for object flow activities, I'm not sure. Okay, diagrams. Okay, so I mentioned a little bit ago that diagrams are coming up, and I would explain how all these elements that we've discussed so far are able to be used. So I'm going to kind of rush through some of these because I'm running out of time. But basically there's two types of diagrams, structure diagrams and behavior diagrams. The behavior diagrams really could be split into two different kinds of behaviors. One is more like interaction type behavior, and the other one is more definition of behavior. So let's just get into this. First, structure diagrams. First diagram is a package diagram. I alluded to that earlier. It contains package elements, and they can be nested. There can be dependencies between them. This shows a deployment model, and by the way, I use different tools for some of these different diagrams. Some of them I downloaded from the internet. I tried to cite where I got them from in the lower right-hand corner of the slide. I don't know what tool created this. There's it basically in the upper left-hand corner it labels a package called deployment model, which has 3 nodes. The 3 nodes are called out in the upper left there, but they're also shown as folders inside the outer folder. and so, two of them actually have folders inside of those folders, and you can see what their contents are. In this case, I believe they're files inside of the inner folders. So you can see sort of a hierarchy here. You can also see that the topology folder uses, whatever that means, to the designer, the artifacts and nodes folders. Okay, class diagrams. We kind of covered a lot of this already, so I'm not going to stick on this too long. Just sort of looking around, if you look at the bottom, in the middle, there's something called signal bait taken. It's shown as an actual class. The reception on the upper left is an operation, and basically shows that it handles the bait taken signal. The bait taken signal itself is a class as well. You can also see that a spring, there could be a humane spring or a deadly spring, depending on the force index which is forced into that. It's a private initialization of that force index variable. On the left, you can see that there's two kinds of bait: peanut butter bait and cheese bait, and they have different odor attraction indices. And I think everything else we've kind of covered already, so I'm going to move on. A composite structure diagram. This is basically to show what larger parts are constructed of or contain or own. These are two different ways of representing similar things. I don't believe that these are exactly coordinated with each other. I don't think they represent exactly the same things, but I think they're close. So there's a car class. A car class owns two rear wheels, and it also owns an engine, which is labeled E on the left. It's also labeled E on the right. The dotted line in the right diagram shows that the rear wheel, the axle, and the engine are all contained in the car. The dotted line represents the fact that it is not composed of an engine, so it's replaceable in a sense. Obviously, the two rear wheels are replaceable as well. In fact, all the parts in a car are probably replaceable. I just was using this example to show the differences. You also notice that there's stars to the left and right of the axle association in the left-hand representation. That represents multiple engines and multiple wheels. Kind of doesn't really make sense. In the right-hand example, you see a 1 and a 2 representing one engine and two wheels. Where it says wheel bracket bracket 2, I'm not sure that that's necessarily a valid syntax. Object diagrams. So object diagrams focus more on the instances of classes rather than on the classes themselves. However, classes can be shown in the diagrams. Instances have instance names and show the relationship between them, between the instances. They show specific attribute. They can show specific attribute values. A lot of this is very flexible. You know, it's not required to do everything. Obviously, certain flexibility allows you to do different designs in different ways. So in this case, you see the lines connecting the instances. You have a customer instance on the top, which is an instance of a customer class. And then you have order 1, 2, and 3 on the bottom, which are instances of the order class. So the same class coordinates the data and operation, data and behavior, I'll say, for the three orders on the bottom. So they all have to have order numbers and they all have to have order amounts. But the instances have different order numbers and amounts from each other. The customer class on the top is related to the ones on the bottom, although this diagram doesn't say how they're related. You would imagine that the orders are for that particular customer. Remember that the association between the customer and the order may itself be an attribute. So it could be an attribute of the order class even. So there might be a customer attribute that has customer 1 as its value for all three of these classes. So customer 1 being the instance value of that attribute. Notice the underlying name for the instances and the default values. Component diagrams. So the idea of a component diagram, this is showing hardware here, but it doesn't have to be hardware. It could be a software component like a DLL or a module. And the component diagram, the idea here is to build up larger components from smaller components. or build up larger entities from smaller components. And it's meant to identify the components, show the relationships between them, show what's internal, what's external, what the interfaces are between the components, not just the relationships. And you can get into as much detail or as little detail as you want about the relationships or structure of the components. That's what the plain bullet means there, that you can just have associations between them, or you could have specific types of associations between them. Connections between, okay, I already mentioned that, and then the connections through the ports, which I've already discussed. So this is meant to show some different ways to represent components and their interfaces. So you have a provided interface, a required interface. Note that the top two do not connect through a port, so it's not required that you connect through a port. However, if you want to indicate a port, that's a good way to go, and you can do that. This is what a typical component diagram might look like. You can see different relationships and dependencies, well, not dependencies, relationships between the interfaces and the components, provided, required, and so on. And I think the idea here is mostly to show external interfaces of the application component, which if you look at the top, the large rectangle, if you look at the top middle, you can see a title for that, or the class name and an instance name and a class name. I take that back. The application components, okay, this is a good example here. So the application components name in the outer large rectangle represents something called a namespace, and you can see the colon is sort of showing that it's the policy administration that it's talking about is the one in application components. Those namespaces can relate to packages, for example. So I think we've discussed most of this stuff. You can see some useful stereotypes. There's on the upper right, the small outer component is stereotyped as a COTS or a commercial off-the-shelf component. There's an LDAP component on here. I don't see any other types. So moving on, deployment diagrams. Deployment diagrams that are meant to show what the deployment context of nodes of a larger system usually, and their relationships. So you can have physical nodes that communicate through links. This is especially useful when the system that the design of the system that you're trying to represent is configurable. So, for example, setting up a particular LAN, for example, and we saw the sort of humorous deployment diagram on the previous slide. I don't know if that's actually a deployment diagram, but it was meant to get across the idea of deployment. In this case, there's clouds and there's electronic link, whatever that is, the thing is in the middle. This is not UML, and I want to make clear that this is not UML. But you get the idea that you can get these big systems that communicate via links, and you want to write them down in some kind of pictorial way. UML is good for that in terms of deployment diagrams. So the artifacts that are stored in nodes, as well as the interconnection between the nodes, are presentable here. Okay, and I think the rest of this slide is okay. So mix and match equipment. The point of that bullet there is to show that you might have equipment that interoperates in different ways. So the same nodes might communicate differently. You might have the ability, those nodes might be able to talk through a serial port, a parallel port, or a TCP/IP port. And you can show different scenarios of how you would deploy equipment using a deployment diagram by stereotyping the connections between them, for example. So nodes, what are nodes? Nodes are physical entities. They may be containers for artifacts, hardware, software, data components, software components. Nested, they can be nested. And they can have something called deployment specifications that describes how they're deployed. So it'd be data concerning how they're deployed. For example, an INI file might be a way to configure the software inside of a node. So the INI file might be an artifact that is the deployment specification for that node. database servers, PC containing software applications, ROM, printed circuit boards, and printers are all examples of nodes. And ports, as I mentioned earlier, are physical connections for communication between nodes. So deployment descriptors, this is something I'm not really well versed at. I mean, it's just a concept I'm trying to present here. I may or may not be presenting this well, but I'll try. A deployment descriptor is a class that has properties that describes a node or artifact deployment. It's instantiated to create a descriptor artifact. Artifacts contained in a node. Artifacts are contained in a node. So in other words, the descriptor is contained in the node. So examples might be configuration files, like I said, an INI file, for example, or some kind of an XML file containing dependencies for IOC apps. Could be anything you want it to be. And again, the idea here is to provide a notation that allows you to convey and express your design ideas in a fairly standard way so that other people can understand them. So this is an example of a deployment diagram and shows sort of the relationships between a client portfolio server and a quote server, as well as a trade server, obviously a financial application, and shows different components. So there's an executable component in the client, and there's also a configuration component, which would be the descriptor, the deployment descriptor we were talking about. There's a quote server that has a vendor component in it, whatever that might mean. Maybe that's a data component. There are several executable components in the portfolio server, and there's a database server component in the trade entry server. Let's see. So this is another example of a deployment diagram. I took this from our functional safety book, Exodus functional safety book, and is meant to indicate a transmitter, show the design, rough design, the deployment diagram design of a transmitter, basically showing that a transmitter has a sensor port, has a current output, that the current output is, you could label that arrow to the right of current output system as a 4 to 20 milliamp stereotype, for example. It has a HART modem, so those two signals are combined together in the current output port to have both protocols going over the same signal connection. The color coding is meant to be functional safety specific, so I won't talk about that. The communication paths between them are meant to show data or signal flow between the elements. You can see that the microprocessor system in the middle has that little chain link down the right-hand side there. That's meant to show in Enterprise Architect, the tool in which this diagram was created, has another diagram that describes its internal structure, or definition, specification, whatever you want to call it. The microprocessor system also has a watchdog and reset port, which are connected to the trigger and shutdown ports of the watchdog hardware. So you can see that this can be used to show not just software structure, but also hardware structure. If we dive, I don't know if we actually dive in, we don't. So if we dove into the microprocessor system diagram, you might see software components inside that microprocessor system component, and how the how the software is connected to the actual physical connection of ADC, PWM ports, watchdog port, the reset port, and so on. I can see we only have a couple more minutes left, so I'm going to kind of try to rush through the rest of this a little bit. This is another deployment diagram example. I didn't get into behavior diagrams. This is a use case diagram. Use cases used for high-level functional analysis of a system. The outer box represents the scope of that system. The inner ellipses represent actual use cases, and the actors involved in those use cases are described by the stick figures there and related to the use cases they interact with. Use case can extend another use case and can be used by another use case. and I'll sort of quickly go through the remainder of these. I don't want to spend too much time on use cases. This is what a use case might look like in terms of how you specify it. Sequence diagrams are useful for diagramming events going back and forth and interactions between two or more classes or instances or any other kinds of objects. The dotted lines in the middle represent lifelines. They're labeled with an instance or class name at the top. The alt box that you see there is meant to be sort of an if-else condition. There's various different ways of handling those sort of sub-sequences. Then the arrows going back and forth between them represent calls to, in this case, calls to a class and returns from a class. Because the C2 object is in the middle there, it's sort of created, and that X at the bottom of its lifeline represents destruction, so construction and destruction of class instances. The labels on the arrows represent the operations that are called on that object. So foo is called on C2 after it's created, for example. The conditions for the if and else are X greater than 0 and the else that you see there. So that's a sequence diagram. Oh, I wish I knew that was there. I would have paged forward. Communication diagrams are basically the same kinds of things, except instead of focusing on the sequence of events, they're more focused on the relationship between the objects. So the call or event that happens between them is labeled with a number, and you can see the 1 and 1.1, A, B, and so on are labeling in a hierarchical way when the events occur. So 1.1A happens after 1, but before 1.1B. And then the actual call is also labeled there. State machine diagrams are another very useful diagram, and basically consist of transitions, states, and can be partitioned. They can also be hierarchically organized into sub-machines, sub-state machines. Very powerful mechanism, especially if you're doing code generation. So this is meant to be a representation of a transition, and it's labeled with a trigger event, a guard condition, and an action. States they basically model some state of an object. So, for example, a class might own a state machine. That state machine dictates through its own state variables what state it's in, and dictates how it behaves when it receives transition events. So transitions have, as I said, source state and a target state, and they also have an event trigger that tells them when to transition or how, trigger on this event. They have a guard condition that even if the event occurs, it still may not trigger because that's a condition that says only transition if you're in this condition, and it has an effect. So during the transition, it may actually execute behavior that's outside of the target state or the source state. And there's a run to completion concept, so this handles sort of queuing events so that when transitions happen, quote, simultaneously, there's a way of arbitrating that. So I guess I'm sort of wrestling with myself here because I'm running out of time, and I think what I'm going to do is just sort of really rip through these, and I apologize for not timing it better, but I wanted to try to get as much information to you as possible. This just talks about different aspects of state machines and how you can use them hierarchically, entering and exiting states. This shows some of the forking and joining, so you can do simultaneous states, parallel states. This is an example of a course in which you have to take a lab, you have to do a term project, and you have to pass a final test in order to go to the passed substate. I gave a traffic light example. Activity diagrams are sort of like, as I said, they're flowcharts on steroids. Their purpose is to basically show interactions between things. And you can see that there's diamonds here for conditional control. There's fork and join to show parallel processing. There's an object node at the bottom to rectangle, and they show basically how you enter an activity and how it runs to completion. Excuse me. Okay. Actually, that's it. That's pretty much all I had for you. If you have any questions, I'd be happy to answer them. I don't have a slide that has my email on it, but if you want to reach me, my email is dbutler, dbutler, @exita.com. I've enjoyed giving this presentation to you, and I hope you got a wealth of information from it. Thank you very much.